So now let's talk about another strategy, another test that we apply only to alternating series. And alternating series look like this. It's either -1 to the power of n times a sub n. By the way, -1 to the power of n makes your series alternating, or something like this, where it's still alternating. The exponent is n plus 1. Now, we say the alternating series converges if both of the following conditions are satisfies the following: limit as n approaches infinity. It looks like just another regular nth term test. So you take the limit, and obviously without -1 to the power of n, and see if it approaches 0. If it does, move on to the next step, next condition. Your a sub n is supposed to decrease. If it's decreasing, a decreasing sequence, then, by the way, where, n plus sub n plus 1 is less than or equal to a sub n for all values of, for all integers. Now the whole numbers are integers. Now, if these two steps work, two conditions work, then you conclude that your series converge. So I want to show you example 16, and probably I'm going to start with number 16a. And it says you have this alternating series n plus 1. Now it goes n over 2n minus 1. So let's see. So we're going to focus on this part. So let's check the first condition. Take the limit as n approaches infinity, and n over 2n minus 1. Let's see if it's 0. Well, it's not 0. It's 1 over 2. So therefore, you stop there and you say this sequence, this series diverges. Okay. B. N over, now it's ln of 2n. So again, let's focus on this part right here. Take the limit, see what happens. As n gets bigger and bigger, ln of 2n gets bigger and bigger, the numerator gets bigger and bigger, so it's infinity over infinity. You can apply the L'Hopital's rule. Take the derivative of n, you get 1. Take the derivative of ln 2n, you get 1 over 2n, times the derivative of 2n, which is 2. And you flip it, that becomes n. Well, and when n gets bigger and bigger, the value of this approaches infinity, so you stop there. We have series that converges. Now, part C, n equals 1, infinity. Now it's cosine n times pi over n. Okay, so first of all, look at this part right here. So when n is 1, you plug in 1, you get cosine of pi. Cosine of pi is -1. Then when you plug in 2, you get cosine of 2 pi, but cosine of 2 pi is 1. Then you plug in 3, you get -1, and then 1 again, and so on. So you can tell that we're dealing with alternating series. So in that case, you need to check those two conditions. So take the limit as n approaches infinity of 1 over n. So you ignore this part right here. And yes, as n approaches infinity, you get 0. So check. That's a good sign. So we're getting there. Now let's check the second condition. Your sequence 1 over n is supposed to get smaller. It should be decreasing. So let's see. And the condition is this. It's supposed to be, this inequality is supposed to work. So if you do that, let's see if it works. If you add 1, obviously the whole fraction becomes smaller. So yes, it does work. So that means this sequence converges. The next example, number D. So we're going to just consider first sequence 1 over n factorial as n approaches infinity, and I can rewrite it as 1 over, so what's n factorial? It's n times n minus 1 times n minus 2, n minus 3, and so on, right? So as n gets bigger and bigger, the denominator gets bigger, the whole fraction becomes smaller. So the first condition works, so we can conclude that this series might converge by the nth term test. Now we need to check the second condition, and just to see if this sequence is smaller than 1 over n factorial. And it is, because this one is n plus 1 times n factorial. And this one is only n factorial on the bottom, so this part right here makes your denominator bigger, the whole fraction smaller. So yes, it is, the second condition also works. And that means your whole series converges.